Welcome back. This is video lecture 32.2, and we're going to be discussing sections 2 and 3, which is going to introduce another aspect of electromagnetic induction, kind of the mirror image of what we learned in chapter 30. And what we learned in chapter 30, the concept often called Faraday's law, is that if you have a changing magnetic flux through a loop, there'll be an induced EMF in that loop and an induced electric field around that loop. So a rather loose way to say it is a changing magnetic flux induces an electric field. Around in the 1800s, somebody thought, could I turn that around, that idea? If I have a changing electric flux through a loop, will there be an induced magnetic field? And that idea turned out to be, that question turned out to be important because the answer is yes. So we're going to talk about what's called Maxwell's law of induction. This is named after James Clerk Maxwell, who made the argument that I just described to you. Maxwell also introduced the concept of what we're going to call displacement current, but we'll have to get to that step by step. Let's start with what I basically just said. All right? Faraday taught us that if we have a changing magnetic flux through a loop, that will induce an electric field around the loop. Faraday's law, empirical fact. Then the question is, shouldn't a changing electric flux through a loop induce a magnetic field around the loop? James Clerk Maxwell felt like it had to be the case. Okay? So here I have drawn a very schematic mathematical loop. Think of that as a circle, a circular mathematical loop. You're looking at it kind of from a perspective. And there are field vectors piercing the inside of that loop, the surface that is the interior of the loop. And that gives you a flux, and that flux is changing with time. In the Faraday's law case, if this is a magnetic field, B, piercing the interior of the loop, then it'll be a magnetic flux. And if that's changing with time, d phi sub b dt, you'll have an induced electric field around the perimeter, either one way or the other, depending upon whether the flux is increasing or decreasing. And that's what this equation is right here. The integral of E dot ds around the loop, and that E is the induced E, is equal to negative d phi sub b dt. Faraday's law. Okay? Now Maxwell said, just turn everything around. Now you still have that mathematical loop. Think of it as a circular loop. Now the field that's piercing the interior of the loop is an electric field, so that we're talking about electric flux through the loop. And what if that electric flux is changing with time at a rate d phi e dt, right? Time rate of change of electric flux through that loop. Then you will have an induced magnetic field around the loop, either one way or the other, depending upon whether the flux is increasing or decreasing. Right? So we just swap the roles. And this is a very important insight in the history of electricity and magnetism, because what it's really emphasizing is that those two fields that we've really been treating up until chapter 30 as being completely different things, electric field, magnetic field, are actually very tightly connected. And in a very loose way, for either E or B, a changing one of those induces the other. A changing E induces B. A changing B induces E. They are interwoven. Okay? And the more you study physics, the more you will see how deeply interwoven they are. All right, but here then is Maxwell's, if you like, law of induction. Just like Faraday's law of induction talked about induced electric fields, you can have a version for an induced magnetic field. We'll call it Maxwell's law of induction. And it says that if you integrate the magnetic field around a closed loop, that'll be proportional to the time rate of change of the electric flux. And then Maxwell made an argument, and we're going to go through that argument in a moment, for what the proportionality constant should be. And it turns out it can't be just anything, because we already have learned a lot about how electric fields behave and magnetic fields behave. And as you recall, almost every time we worked with an electric field, that constant epsilon zero was around. And every time we were working with a magnetic field, that different constant mu zero was around. And now that we're saying how they're interwoven with each other, what Maxwell found is that the proportionality constant in this equation is actually the product of those two constants together. And that's the first time we've seen them both together in the same equation. And that is, it turns out, a clue to something very profound about electric and magnetic fields, which we will learn in the next chapter that we study. But for now, we're just going to take this as a correct statement of nature, Maxwell's law of induction. The integral of the magnetic field around a closed loop is equal to mu zero, the permeability constant, epsilon zero, the permittivity constant, times the time rate of change of the electric flux through the loop. We're going to apply that to a situation we've studied a lot because we're so familiar with it. A capacitor, a parallel plate capacitor hooked up in a circuit, and we're going to be looking at the situation where the capacitor is in the process of being charged up. Right? The simplest way to think of it is we've taken the parallel plate capacitor and we've taken wires and we've hooked them up to a battery or a power supply. The battery or power supply will do work, and mobile charges will move around, and we will have conventional current I flowing through the wire such that there is positive charge Q building up on one plate, we'll say the top plate, and then the conventional current flows downward on this wire so that we have an equal negative charge minus Q on the bottom plate. Okay? We'll take the plates to be circles of radius capital R. Circular plates. It'll make the geometry easier. And therefore they have some kind of area A, which of course would just be pi times big R squared. Now we know the minute you have two parallel conducting plates, one with positive charge, one with an equal amount of negative charge, you get an electric field in the region between them. And if the plates are close enough, you can assume that electric field in the region between them is nice and uniform. And we're going to assume that. And so we're going to say that we know that there'll be an electric field E in the region between the plates, and it will be pointing downward, away from the positively charged plate towards the negatively charged plate. All in that region between the plates, and no fringing of the field outward, outside the plates. So if I draw electric field lines, I've just got nice, uniformly spaced, downward pointing arrows, or lines with arrows on them, to show a nice uniform electric field in the region between the plates, E. And note, please, technically, that E depends on time, because the charge on the plates depends on time, because we're still in the process of charging the capacitor. All right, so that's all going on, right? But we've kind of discussed that kind of situation. Now, let's imagine a circular mathematical loop right in the center. And it's drawn here in this side view as that kind of purple line, right there. But it's really a circular loop centered right in the middle, okay? And we're going to calculate the electric flux through this circular mathematical loop of radius big R, which means we imagine breaking up that loop into little area patches with an area vector dA perpendicular to the patch, and there's one of them pointing downward. Okay, so what do we get when we calculate the electric flux through that loop? Well, we've got a nice uniform electric field between the plates. We're neglecting the fringing of the field at the edges of the plates. So when we do this integral, E dot dA over the surface inside our circular loop, it does indeed simplify to this nice clean result. Just take the magnitude of the electric field anywhere between the plates times the area A of our loop, which is pi times the radius squared. Now again, we have studied the parallel plate capacitor geometry for ages now, and we already know that using Gauss's law, you can work out the formula for the electric field between the plates of a parallel plate capacitor. So I'm just going to state it because we've used it before. It is that the magnitude of the electric field between the plates is the charge Q, you can think of that as the charge on the positive plate, over epsilon 0 times the area of the plates. Okay? Put that expression for the electric field magnitude, that whole expression, right there in the electric flux formula. Let's see what we get. There's Q over epsilon 0A times the area of the loop A, but that's the same as the area of the plates, so those two cancel, and I'm just left with Q over epsilon 0, the charge on the positive plate over epsilon 0. But remember, the capacitor is still being charged, so this Q right here, that's the charge on the positive plate, depends on time t. And since it does, let's ask, what is the rate of change of the electric flux? d phi sub e dt. Well, here's what phi sub e equals, Q over epsilon 0. So just take the time derivative, epsilon 0 is a constant. You get 1 over epsilon 0 times dq dt, the rate at which the charge on the plates is changing. But wait a minute, where is that charge on the plates in essence coming from? It's coming from the current in the wires, the conventional current I in the wires. And the rate at which the charge is building up on the top plate has to be exactly equal to the rate at which the charge is moving in the wires, because it's coming in. Okay? So that dq dt that you see there, which is technically the rate at which the charge on the top plate is building up, is growing, it must equal the conventional current I in the wire connected to the plate. Does that make sense? Because remember, charge is conserved. It can't just appear magically. All right. So, fine. That dq dt is the rate at which the charge on the top plate's growing or changing. And it must equal that conventional current in the connecting wire. But now go back to think about our actual loop that we're studying. I'll draw our side view of our parallel plate capacitor again. 2 wires and 2 conducting plates. But in the middle, that's our mathematical loop. And what we have happening is we have electric field piercing through the area inside that loop. But our conventional current I is flowing downward in the wires like that. Note then, there is no conventional current through the mathematical loop between the plates, right? There's no I, conventional current, flowing through that mathematical loop, right? The loop that we use to calculate phi sub e. But what Maxwell argued, because he was studying this situation, he said, well, it will be convenient to think as if there is current flowing through the mathematical loop between the plates. Now, it's not conventional current by any means, but he's saying it's convenient to think as if there were some kind of current in the region between the plates flowing through that mathematical loop. Okay? So he's saying, let's think as if there is current between the plates of the capacitor, but so as not to confuse it with conventional current, he gave it a different name. He called it displacement current, I sub D. It's not necessarily a very illuminating name in that the name doesn't really convey anything deep, but he just doesn't want us to confuse it with what we've been calling conventional current. And then, based on this geometry, he figured out what that formula for the displacement current between the plates had to be. Okay? And in fact, it's just this expression right up here, where you think of the dq dt as the displacement current, ID, and when you solve that equation for that, you get this result right here. The displacement current that we're pretending flows between or through our loop is equal to epsilon 0 times the time derivative of the electric flux through the loop. Because there is an electric flux through our loop. Absolutely there is. And it's changing with time because the electric field is changing. And so now what you can do from now on is you can use this formula that I just highlighted in yellow as a general way to calculate the displacement current in any situation where you have electric flux piercing a loop and changing. And we will use it whenever that situation arises. Whenever we have a mathematical loop and we have electric flux through that loop and that electric flux is changing. When that's the case, we will think as if there is a displacement current flowing through that loop, and this is the formula for how you calculate that displacement current. So now let's look at a couple more pictures for comparison. Again, this is a side view, very simplified view, of our parallel plate capacitor and its connecting wires. First on the left, the picture of the real physical situation with the charging capacitor. Conventional current I flowing downward in the top wire and downward in the bottom wire. Positive charge plus Q building up on the top plate and an equal amount negative Q building up on the bottom plate, so the Q is a function of time. And that's producing a nice uniform electric field in the region between the plates that's a function of time, as long as the capacitor is charging or discharging. That's the real situation. Here is the equivalent situation that it's useful to think about. This is thanks to Maxwell. He said, well, think about it as if you got the two plates of the capacitor, you got the conventional current coming down in the top wire and going away in the bottom wire. You got the top plate and the bottom plate. But then what you've got in the region between the plates is a nice uniform distribution of displacement current, ID. And the way to calculate that displacement current in that region between the plates is to take epsilon 0 times d phi e dt. And when you account for all the displacement current between the plates, you will discover that the displacement current between the plates, ID, is equal to the conventional current, I, in the wires that are carrying the charge that's charging the capacitor. An analogy that I will offer to you, if it helps, to think about that situation on the right. I like to think of it sometimes as almost like a plumbing analogy, a water analogy, like in a shower. And the top wire is actually a pipe with water coming down. And the top plate is a shower head, one of those big flat top shower heads that produces rain in the shower coming down at a steady rate. And the displacement current is all that rain that's coming down from the shower head. And then the bottom plate is the floor of the shower. And in the floor of the shower, there's a drain. And the water then goes in the bottom wire is actually another pipe for the drain water to go down. And you can't gain or lose any water. So the total rate at which water is coming down in the top pipe has to equal the total rate at which water is raining down in the shower, has to equal the total rate at which water is going down the drain. Can't gain or lose any water. That's a way to think about it. Okay? All right, now, with that new idea about displacement current, whenever you have a loop with changing electric flux, we can go back to an idea we've already had and note that it has to be modified now. The idea we have to go back to is Ampere's law. Let me remind you of how we learned about that in chapter 29, Ampere's law. When you integrate magnetic field around a closed loop, choosing the loop of integration, the result will be proportional to the conventional current enclosed by that loop. Conventional current now, I'm emphasizing that. And the proportionality constant is mu0. And what Maxwell realized is, well, we have kind of a new kind of current, displacement current, which is really just going to arise whenever you've got a changing electric flux through your loop. But what Maxwell argued is, well, just like conventional current produces magnetic field, displacement current can produce magnetic field. And so all you have to do to get the correct new version of Ampere's law is include another term on the right-hand side. So on the left, you still say that you integrate the magnetic field around a closed loop, and we pick the loop. But now we're saying that the result of that integral will be proportional to the sum of the conventional current enclosed by the loop and the displacement current enclosed by the loop. And again, the proportionality constant is mu0. So Maxwell added that displacement current enclosed term. Okay? And then all I did in the next line is write down the formula for calculating displacement current. Epsilon 0 d phi sub e dt. And so we might call this now the Ampere-Maxwell law, because it was Ampere's law with another term put in on the right side that Maxwell deduced needed to be there. Okay? By the way, you may have been wondering, well, if Ampere's law was missing something all along, why didn't we worry about that in chapter 29 when we first introduced Ampere's law? Why did we use Ampere's law in a way that apparently wasn't correct? Well, it's interesting. It turns out this new piece that Maxwell added is in almost all situations extremely small. After all, look at this expression I just mentioned for the displacement current, epsilon 0 times d phi sub e dt. That, remember epsilon 0's value in SI units? 8.85 times 10 to the minus 12. 10 to the minus 12. Think about how small that number is. Notice that factor of epsilon 0 is present in the displacement current, but not in the conventional current. Because of that epsilon 0, this term that Maxwell added is in almost all situations extremely tiny. In fact, generally speaking, about 12 orders of magnitude, 12 factors of 10, smaller than the conventional current term. And so Ampere's version is almost always perfectly acceptable. What Maxwell realized is that, well, okay, that's true, but what if you have a situation where it's highly specialized, but it does happen in the region between the plates of a charging capacitor, where there is no conventional current at all, but there is changing electric flux? Then the only game in town is the displacement current, and then you can't ignore it. And that's what Maxwell realized. And that was one of the, I really don't think it's overstatement to say, in the history of science, one of the most profound insights ever. Because it has, it turns out, implications for technology that are absolutely earth-shattering. All the technology associated with electromagnetic waves and the electromagnetic spectrum, we will learn, comes from this new idea from Maxwell. Now here's just another view, okay? Just a different way to draw it, a little bit more of a perspective view of wires and the two plates, two circular plates of a parallel plate capacitor that is being charged up. Just to emphasize how we're going to think about it now. If we have a charging capacitor in a circuit, in the wires we'll have conventional current, in this case flowing to the right, with plus charge building up on that plate, and equal negative charge building up on that plate. And that we can think of there being a displacement current, nice and uniformly spread in the region between the plates, flowing to the right, in this case, away from the positively charged plate towards the negatively charged plate. And the total of that displacement current equals the conventional current. ID total equals I. Just think of it as currents in the wire, then spread out uniformly in the region between the plates, and then in the wire again. But current produces magnetic field. So what is the resulting magnetic field that comes from these currents that we see? And we're going to look at that in three places now. First, at a point to the left of the capacitor, in a region, okay, right about here. And I'm going to assume this point, by the way, is pretty far to the left of the capacitor. And so what I've really got then is just a long straight wire carrying current to the right, conventional current. We know a long straight wire creates magnetic field, and it circulates around it according to a right-hand rule, and that's what this green circle is showing. Let's call this B in the magnitude there, B1. And we know that magnitude. We know the formula. B1 is mu 0 I over 2 pi r, where r is that distance from the wire out to the point where we're finding the field. And that is also true at this point over here. That's pretty far to the right of the capacitor. And over here I just have a long straight wire with conventional current to the right. And so I get the same B, B1, mu 0 I over 2 pi r. Okay? Conventional current producing magnetic field, long straight wire. In this case, we know the formula. What about if we happen to be located at a point that is lined up with the gap region of the capacitor, but just beyond the edge of the plates? Okay? Still that distance is r from the center. Is there a magnetic field in there? You bet. But what's it due to? It's due to the displacement current that's flowing in the whole region between the plates. But we would still apply an Ampere-Maxwell law calculation to the loop here. See it? We would integrate B dot ds around that loop, and the answer must equal mu 0 times the displacement current enclosed by the loop. Because for this loop now in the middle, there is no conventional current piercing it. Because remember, we're in the region between the plates. There is displacement current. Now, it so happens that our loop here encircles all of the displacement current. All of it. So you can just write that as ID. And that ID is numerically equal to the I in the wires. Okay? And if we call the magnetic field in this region B2, you can use this result to solve for B2, and it has the same form as B1, except you're using the displacement current. And so we can use this modified Ampere's law for these three various loops to find the magnitude of the magnetic field due to either conventional current I or displacement current ID. Note you can use this approach. Let me draw, I'll draw up over here. I'll try to draw. Oh, that's pretty bad. A perspective view. One plate, other plate, wires with conventional current I, like so. What if I pick a point in the region between the plates, but only part way out? So now this distance r is less than the radius of the plates. I can still apply the modified Ampere law to a loop and integrate around and use this result right here. But I have to include then only the displacement current that is encircled by the loop. Right? Only the displacement current that pierces that area, which will be some fraction of the total displacement current. And you can figure out that fraction if I tell you the radius little r of the loop as well as the radius big R of the plates. I'll let you think about that a little bit, okay? All right, so what I'm going to leave you with in this video is now a statement that really represents some very profound physics. It is the four main equations that describe the behavior of electric and magnetic fields. And as far as we know, there are no exceptions to these results. They are grouped together collectively and called Maxwell's equations of electromagnetism, even though a lot of people were involved. Maxwell was the one who kind of put them together and showed how some of them were connected with each other, and then deduced new implications from that. But here we are. What are the four equations of electromagnetism? In no particular order. They're not in order of importance. They're all equally important. The first one we'll mention, Gauss's law for electric fields. The integral of the electric field over a closed surface integral, equals the enclosed charge over epsilon 0. The version of Gauss's law for magnetic fields. The integral of the magnetic field over a closed surface will always equal 0. Next, Faraday's law for electromagnetic induction. The integral of an electric field around a closed loop. Be careful. You've got to distinguish mentally between whether we're talking about a closed surface, like the surface of a blown-up balloon, or a closed loop, like the surface formed when you take the two ends of a string and tie them together. Now we're talking about the integral of the electric field around a closed loop, and that will be equal, to the negative rate of change of the magnetic flux through the loop. And then the Ampere-Maxwell law. The integral of the magnetic field around a closed loop is equal to mu0 times the conventional current encircled by the loop plus mu0 times this is the displacement current encircled by the loop. Okay? Epsilon 0 times the time rate of change of the electric flux through the loop. We will be talking about this in class. So I will leave you with a class engagement exercise. On Blackboard. Okay, that goes like this. It's about displacement current created by circulating magnetic field, or correlated with. All right, now it's really clear, it's really important to be clear what we're looking at here, because it looks a little odd perhaps to you. What this figure is showing is a view of one plate of a parallel plate capacitor. That's the shape in gray. Yes, it looks like Mickey Mouse. They're just kind of being whimsical here. It's one plate of a parallel plate capacitor, and you are looking at it from a vantage point of being between the plates. You are inside the gap of the capacitor. Okay? You are inside the gap of the capacitor, looking at one of the two parallel plates. And yes, that's the shape, the Mickey Mouse shape. All right, we have dashed lines that you can see showing 4 integration paths or loops. They're labeled A, B, C, and D. You may think of path B as following right on the edge. I know it shows it a little bit inside the edge. You can think of it as being right on the edge of the plates. You are to rank the paths according to the magnitude of the integral of B dot ds along those paths, and we are looking at the case where the capacitor is discharging. And we want to, so we're ranking the magnitude of that integral, biggest to smallest, for those loops. See, A is the small one, B is next, following the shape of the plate, C is bigger, but follows the shape of the plate, and D is just a big circle. And you are inside the capacitor in the gap, looking at one of the plates, and the capacitor is discharging. Rank the values of B dot ds. Okay, so that's all for this video, and we'll talk about these ideas in class.